Welcome back to the second part of the nonlinear systems. So, today we will see what are the different types of nonlinearities, or what are the different uh, common, or what are the common nonlinearities that we see. Okay. Before going into that, we will see why we are going for this nonlinear control. You can in fact pause the video and then you can think about what are the reasons behind which we are going for this nonlinear control, or we are learning this nonlinear control. Okay. So okay, I hope you have thought about it and then we'll see why it is so. So, in the last sessions, we had seen that usually real systems are in fact nonlinear in nature. Okay, so in order, and we what we had been doing is we had linearized the real systems, and we had tried to design controllers for the linear part, linearized version. Okay, so now what we are in the case of nonlinear control, if we are introducing nonlinearity or more physics to the system, if we are trying to introduce more physics to the system, what we are doing here is more physics to the system. That means if we are introducing more nonlinearity to the system, we are trying to improve the existing control systems that we have. Okay, we are trying to improve the existing control systems that we are having. And the next thing is we are also going to deal with model uncertainties in the system. That means when we had been trying to model a system, what we did was we had forgotten about the uncertainties that come in model while modeling the system. Okay, so that was something we had neglected. We had neglected those uncertainties because we knew that there would be some nonlinear terms in the while which will come during modeling. Okay, so without considering those uncertainties, we had modeled the system and designed controllers for the system. Okay, then the next part that we can do is when we consider all these things, we come up with a better performance for the system. Better performance, which is even cheaper than the previous system. Okay. So these are some of the reasons why we go for nonlinear control systems. Okay. Now we will go to the next session. That what are the different types of nonlinearities that we see or we had come across, and one is a hard kind of nonlinearities and the other one is a soft nonlinearities. So hard nonlinearities is something which are caused due to discontinuities in the derivatives. Okay, that is, if there is a discontinuity in the derivative, in the derivatives. Okay, for example, I can show you a picture here. For example, if I consider a function like this, we can say that this is continuous. That means there are this is differentiable at every point. Okay, that means we can take the derivative of this curve at every point. For example, if I consider a function like this, that means it has a discontinuity at for example at 1. It has a discontinuity here. That means I cannot take the derivative at this point. For example, if I can consider the mode x function, there is a singularity here. That means there is a discontinuity here. So this kinds of nonlinearities are in fact called hard nonlinearities, which we come across in systems. Okay. So this has to be considered by modeling and designing controllers. Okay. And the next, another kind of nonlinearity that we had neglected was the soft nonlinearity. That is, if you come across a soft nonlinearity, that means, for example, e raised to at. Let me write e raised to, if we write it as a series, I can write it as 1 plus at plus 1 by 2 factorial a squared t squared plus etc. etc. If a is very small, what we used to do is we used to say that Okay, we will neglect all the higher order terms, and then we had been doing this because we wanted to end up with something which is linear in nature. Okay, so these kinds of things that we had been doing in many cases. And another example is I would like to quote here is the example that we had seen in the last class: mx double dot plus b into x dot plus k1 into x plus k2 into x cubed equal to some f. Okay, so in that case, this is a nonlinearity that is introduced in the system. X cubed introduces a nonlinearity to the system. For example, if x is a very small value, very small, yeah, if we are considering for a very small range of x, we can say that this term can be neglected. Okay, this term can be neglected for small value of x. Small x, we can neglect it. But for higher values of x, we cannot neglect it. Okay, so for many systems, if we are working in a small range of operations, this linearizing the system may work. Okay, so non-linearity in the case if we introduce if we are learn if we learn more about non-linear systems, what we can do is we can work in a large range of operations. Okay, range of operations. That is another thing that I would like to point here. Okay, now the next thing is like we had seen what is a hard type of a nonlinearity and a soft type of nonlinearity. Now we will try to classify this hard nonlinearities. We won't be dealing much with the soft nonlinearities except for drawing one or two face portraits, uh, if possible. And otherwise, we will be dealing with the hard nonlinearities. Okay, so hard. If we classify the hard type of nonlinearities, we can say that they can be classified as incidental and intentional nonlinearities. Okay. Incidental nonlinearities are those kind of nonlinearities which are already present in the system. For example, the saturation, Coulomb friction, deadzone, and backlash. Saturation, I'll explain here, means, for example, if you consider the magnetic saturation, it is a property of the material. Okay, friction, that means there is friction between two surfaces. In fact, this is the characteristics of the system itself. Okay, this are already present in the system. Whereas in the case of a relay, we introduce a relay to the system so as to change the characteristics of the system. Okay, we want to change the characteristics of the system. So that is why we introduce a relay to change the characteristics, okay, of a system. So characteristics of a system. That is why I introduce a relay here. And these are the kind of nonlinearities that we deliberately introduce to the system. Okay, introduce in the system. Introduce to the system. Here, incidental are something which are already present in the system. Okay, which are already present in the system. Right here, which are already present in the system. Okay. Now, before going into the different types of nonlinearities, we will also see what is meant by piecewise linear approximation. Okay. Now, if we consider a simple curve like this, for example, if this is the x and y axis, output, input, and the output axis. So I'm trying to draw something like this. Something like this. Okay. So if I want to work with this kind of a systems, this kind of a system is nonlinear in nature. So what we try to do is we try to approximate this linearly. How do we approximate it linearly? I cannot approximate it using a single curve, because here it is going down, here it is going down, almost down, and then going up. I cannot approximate it using a single curve. So what I will try to do is I will linearize it piecewise. For this part, I will linearize it like this. For this part, I will make some linearization like this. for this part, after this part I will linearize it like this, after this part I may linearize it like this. So I make piecewise approximation to this whole function. So this kind of approximation is used to numerically solve the problem, and it in fact is seen to work very fine. You know, like and for in fact we can also reduce the range of this function for which we linearly approximate this function. So we usually get very good results also when we do this kind of an approximation, and they do that when the complexity of a function increases. Okay, so this is called piecewise linear approximation. Okay, and now we will go to the major part of today's session, which is the what are the different types of nonlinearities that we see. Okay, first we will see the common nonlinearity that you all know, which is called a saturation type nonlinearity. For example, if I want to consider the magnetic, if I change the current through a system, and if I try to see how much it has been magnetized, we can see that initially it magnetizes, the magnetic material magnetizes linearly as we go on increasing the current through the system. Linearly means almost linearly, and after some time it saturates, and then it becomes a constant. Okay, even if we increase the current further, we cannot the we cannot increase the magnetization of the magnetic material. So that means it has saturated. So this is in fact a kind of nonlinearity that we have introduced to the system. Okay, if you try to reduce the current, it decreases in the opposite direction, and also we can get it something like this. Okay, so if I try to draw straight line curves for this kind of system, I can draw it like this, something a straight line like this. Here also I can draw it like sorry a straight line, something of this form. Here also I can draw it like a straight line. So the white line is the actual curve. So here it becomes constant, showing that there is saturation. This is the input and the output. So in general, we can say that even initially it is almost linear. Okay, initially for some part of the, as we go on increasing the input, we can see that the output is linearly increasing, but after some time, even after, even if we go on increasing the input, there is no change in the output. That means there is saturation happening here. Here we have a saturation that is happening here. So this is saturates. Okay, the system saturates. Okay, now we will go and see the next kind of nonlinearity, which is friction, which is a friction nonlinearity, which you all know all these kinds of things, but we will see it in a different way. For example, there are three types of friction. One is called stiction, one is stiction, and Coulomb friction, stiction, Coulomb friction, and viscous friction. Viscous friction. Stiction is also called static friction. This is also called static friction. Okay, we'll come to that. So first we will see the viscous friction that we had seen in fact in linear system. So I will start from C and then go to A. Okay. So in linear systems, when we had studied the mass spring damper system, what we had seen is, we had seen the equation m x double dot plus b into x dot plus k into x equal to some force we had applied. So where in when we had dealt with this kind of equation, we had said that this term is in fact we have to consider it as a viscous friction, so that we can write a linear relation here. So in the case of a viscous friction, we can say that it is because of the relative velocity. X dot is the velocity here. Okay, it is caused because of the relative velocity of sliding surfaces. If there are two surfaces here, if this is a mass and if this is a mass here, and this is a mass here, and this is a surface here, and if this is moving here, what happens here is there is a viscous friction between the surfaces. Okay, so that is called that is linear in nature. So we can draw the linear curve like this. If this is the input velocity here, okay, I will draw it with the same color, different color here. If this is the input velocity here, input velocity, input is the velocity. When there is a movement for this mass, what happens is there is a we come across the viscous friction, which is directly proportional to the relative velocity of the sliding surfaces. So we can draw a linear curve here. Okay, so this I can write it as FV. This is the viscous friction, viscous friction. So it is linear in nature. This is what we had seen in a mass spring damper system. Okay, and we had neglected all the other kinds of non-linearities, and we said that we are only dealing with viscous friction here. Okay, and now we will see what is a stiction. Okay, stiction is something, or it is called a static friction. Suppose this is a mass here, this is a mass here, this is the mass, it is placed on a surface, and the mass is at rest. The mass is at rest. Okay, now we require some force to we require a force to initiate a motion to this mass, right? Initiate a motion to this mass, and the friction which is caused, that means the force required to move the mass is called the frictional force required. That means the force acts opposing to this force that is acting against this body. Okay, that force is called the static friction. So stiction is nothing but it is a force required to initiate motion of this mass. Okay, so this is stiction. I will draw it with a red color here. Stiction means, that means the frictional force for a body at rest. I will write it with F of S. This is the input velocity. So there is no velocity for the system. The body is at rest. So that is why for a body at rest, we have a static friction. So we require some amount of force to move it from rest. So that is called static friction against the friction that is acting on the body. That is called static friction. Now Coulomb friction is, suppose I have, now I go and start moving this body. This starts moving. When this body starts moving, what happens is that suddenly the frictional force reduces, and there is always a constant retarding force acting on the system. Okay, so that friction is called a Coulomb friction. That will be a constant force, retarding force, which is acting on the body. Constant force. Okay, it is a constant force, constant retarding force, which is acting on the system. Okay, it's a constant retarding force which is acting on the system. So it will definitely be less than the static friction or stiction, because the body starts moving and there is less friction compared to the static friction. So it suddenly jumps from this point to this point. So this is how, in the case of ideal cases, we can draw it like this. Okay, it jumps from this point to this point and it reaches the constant retarding force suddenly at point 0 and starts moving. In the case, actually what happens is that it is something like this. The curve will be something like this. This is the actual stiction and Coulomb friction case. So something like this. It slowly, this is a stiction value. It slowly moves and comes to this value. Okay, this is how it happens. This is the actual case. Now, once the body starts moving, now once the mass starts moving, what happens to the system? Initially, the body has a stiction in the system. Okay, stiction in the system. So after, once the body starts moving, there is a constant retarding force on the system which is equivalent to the Coulomb friction. Coulomb friction. This is the Coulomb friction. This is a constant retarding force which is acting on the system. So it will come up till here. After that, what happens is that this is the Coulomb friction, it will come up till here. After that, what happens is that the body starts moving. What is left over in the system is, what will be there? It will be converted to viscous friction. Okay, so the total friction in the system will be Coulomb friction plus this viscous friction, which is linear here. So this is a kind of non-linearity that is found in bodies, in moving bodies. Okay, so this has to be considered while modeling the system. Okay, so this is about the non-linearity friction. Okay, now we will go to the next topic, which is called backlash. Okay, backlash is usually, this is a gear, in fact. This is, in fact, we have heard about the magnetic hysteresis, okay, in electric circuits. Here, backlash means the magnetic hysteresis, the hysteresis that occur in mechanical transmission systems. For example, this is a gear train. So it is in fact a part of a mechanical system. We all know about a gear train. That means we are trying to transmit the different speeds from one speed to another speed. Okay, that is why we are using a gear train here. This here, I have shown here a picture here where this is the tooth of one gear and this is the tooth of the other. Let this be the drive gear and let this be the driven gear. I am driving this gear so that I can rotate the other one. This is B and this is A. So when I drive gear A, B will be rotated. Okay, if I drive gear A in the clockwise direction, in this direction, what happens? B will be rotated in the anti-clockwise direction. Okay, this is what is happening here. So if you look closely to the speaker, we can see that when there is a gap between the tooth here. In fact, this gap is called the backlash in gears. So we will see how this backlash is a non-linearity in the system, how this backlash causes a non-linearity in the system. So this backlash is usually provided to avoid the wear and tear here and produce uh, smooth movement for the system. Okay, so now we will see this. I have drawn it separately here. So if you look at this figure here, we can see that this is the drive gear. This black one is the drive gear. Right here, black one is the drive gear, and the blue one is the driven gear. Okay, so I will also draw here picture here. You'll see the graph of what happens in the system. Okay, now this tooth of the drive gear, let it be one, it is at the center of B1 and B2. Let the distance between these, let the gap here be equal to this gap be equal to B by 2. And the gap here, let it be equal to, that also be equal to B by 2. So it is in the center. This tooth is in the center. Okay. Now, if you look closely at this figure, we can see that this tooth has to move a distance of B by 2 to touch the B1 point. Okay. B1 of the driven gear. Tooth B1 of the driven gear. It means it has to move a distance of B by 2. Till then, now the drive gear is rotating in the clockwise direction. So only after it moves B by 2 distance, then only it can initiate a rotation for the driven gear. So it has to move for about B by 2 distance for some time in order to initiate a rotation for the driven gear. So once it starts touching the B1 part of the driven gear, what happens is that the driven gear starts rotating in the anti-clockwise direction. Sorry, I'll draw with the driven gear starts rotating in the anti-clockwise direction. Okay, so it is here, there is no rotation. Here it has not started rotating. Here it slowly starts rotating in the anti-clockwise direction. So now it starts rotating in the anti-clockwise direction slowly till some angle theta. Some angle, let me write it as theta d. That is theta of the theta p of the driven gear. Okay, theta input, I'll write it as theta input. Here we are rotating at theta angles slowly, but it starts rotating only after some time. Now it comes here and it reaches some point theta. So this has rotated an angle of theta degrees. It has rotated an angle of theta d degrees. Okay, it has rotated an angle of theta d degrees. Now in the case of a linear system, what we do is we will see if you try to rotate this drive gear in the opposite direction, what happens? We have to follow the same path. But now we will see what happens in this kind of a gear. So now we will try to, this is in position as shown in figure 2. This is 1, this is 2. Okay, now in figure 2, from figure 2 I am trying to rotate it in the anti-clockwise direction. Yeah, I am trying to rotate the drive gear in the anti-clockwise direction. So drive gear is now at position B1. Now at position B1. So we know that only when it touches the other part, only when the tooth of the drive gear touches the tooth of the driven gear, then only it can initiate rotation for the driven gear. Okay, so now the tooth of the drive gear is at B1. It has to go and touch B2. Okay, so as to initiate rotation for B2, when this drive gear is rotating in the anti-clockwise direction, it initiates rotation for the driven gear in the clockwise direction. Okay, now how much distance it has to move? This was B by 2, this was B by 2. So what will be the total distance? It has to move a distance equal to B distance. Okay, so as to go and hit B2. So it has to move a distance B to go and hit B2. So that means when the drive gear is at position theta d now. Now what happens? It has to wait for a distance B. Sorry, it has to wait for a distance. This is B by 2. It has to wait for a distance B. I think I have chosen this wrong one. Distance B, so that it starts moving again. Then it waits for that much time. There won't be any rotation. That is why it is constant. It is still at theta d. Once it moves a distance B, what happens? This moves a distance B. This tooth 1 touches the point B2. tooth B2. Then suddenly it starts slowly changing the angle. It starts rotating in the anti-clockwise direction. The drive gear starts rotating in the clockwise direction, and then it will reach minus theta d. Okay, again when it reaches minus theta d, so it has touched here and it has started rotating in the anti-clockwise direction. The drive gear has rotated in the clockwise direction. So once it again touches this point, now if we try to reverse it in the opposite direction, if you try to pull the drive gear in the opposite direction, what happens? It has to again move b distance to rotate this in the anti-clockwise direction. So that means I have to again move b distance forward to rotate it in the anti-clockwise direction. So now this again comes, oh, sorry, this comes, it has to be on the same line. Okay, so this is the same line, and this is something which is happening here. This looks similar to that of the magnetic hysteresis that we had seen in magnetic circuits. Okay, this is called the mechanical hysteresis. Okay, so in fact, this kind of nonlinearity, this is a kind of nonlinearity that we find in gear trains. Okay, we usually use gear trains. Why do we use the gear trains? In control systems, we want to transmit some velocity ratios, okay, from one shaft to the another. That is why we are using gear trains. But these gear trains are can introduce this kind of a nonlinearity to the system. Okay, this nonlinearity can cause sustained oscillations in the system. This can cause sustained oscillations in the system. Okay, oscillations in the system. And this can also cause chattering to the system, and also the system can become unstable. Chattering to the system, and system can also become unstable. So these are the difficulties of having. In fact, we introduce the backlash to avoid the wear and tear, and also to run the system smoothly, and in order to avoid the locking between the tooths. But this kind of a system can cause a nonlinearity of this form, or magnetic hysteresis in the system, and this magnetic hysteresis can cause sustained oscillations also in the system, and can even cause the system, bring the system to instability. Okay, so when we are introducing gear trains to the system, we have to introduce this kind of a non-linearity and study the system. Okay, model the system with this kind of a non-linearity and study the system, and then design methods to avoid these instabilities in the system. Okay, that is why we are learning this kind of non-linearities in control systems. Okay, another kind of non-linearities is the death zone. Death zone is something which you all know, right? For example, a simple death zone that I will give you is an SCR. For example, in the case of an SCR, even if we increase the voltage up to a particular level, we can see there is no change in the current. Suddenly, only after a particular time, the current starts increasing. This is in fact a death zone. That means there is no change in the current. Okay, so that means nothing is happening at that point of time. Okay, that this relation between the input and the output is called a dead zone. Okay, this we can write it, draw it something like this. For example, this is a dead zone. For example, if this kind of a non-linearity, I can say this is a kind of non-linearity which is a dead zone, which is usually found in some kind of gearboxes. Gears with torsional spring loads, we usually find this kind of a non-linearity. Okay, so dead zone means there won't be an output even if there is an input initially to the system. The output will act only after some time. Okay, that is called a dead zone. It will be the output will be zero. Okay, and that means this also means that the system is insensitive to the small signals. That means if the input for small input signals, the system is insensitive. That means the system is not showing any output. Okay, this can cause instabilities in the system. We have to study this kind of a non-linearity, and we have to design systems based on these kinds of non-linearities. Okay, to avoid the instabilities due to these kinds of non-linearities. And another kind of nonlinearity is the intentional nonlinearity, which we had said before, which is a relay. This is, in fact, a nonlinear, we can call it as a nonlinear power amplifier. And this whatever I have drawn here is a simple representation of a motor control system. That means I want to rotate this motor in both directions. I'm trying to rotate the motor in both directions. This is I forgot the field here. Okay. I want to rotate the motor in the clockwise direction and also in the anti-clockwise direction. So if a plus voltage is given to the system, let the motor rotate in the clockwise direction. If it is minus V, the motor is rotating in the anti-clockwise direction. Okay. So now like we will see the characteristics of an ideal relay. So this is a relay. So we are trying to energize this. So we give an input to the system. Say we say that I want a speed of n rpm for the system, and equivalent voltage equivalent to n rpm is given to the system, so that I want to energize this coil and act the relay. So what we will see an ideal relay. What happens whenever I give an input, the system this is suddenly switches on to when I give an n RPM to the system, an equivalent voltage acts on the relay coil and it suddenly switches to plus V volt, and an equivalent output I will get. I can rotate the rotor in the clockwise direction. I give a minus, if I say that I want to rotate it in the anti-clockwise direction with n RPM, in the anti-clockwise direction with n RPM, then suddenly the relay coil will act in the opposite direction and it switches to minus V, and then it suddenly comes to this point. This is a kind of nonlinearity. This is in fact an ideal relay. This is a circuit of a this is a graph of an ideal relay, but this is not the actual case. So what happens is that now we can see that there are in fact hysteresis in relays. Okay, so we can see a system, a relay with the hysteresis, pure hysteresis. For example, uh, the relay is switched. Suppose I am switching on the relay due to I have given an n RPM to the system. I'm switching on the relay and it is somewhere here. It switches on and it is having a speed of n RPM. For example, this is the equivalent voltage. I have just written it as n RPM. So this is the input I have given to the system, and this is the output. Output. Okay, so I give an input current to the system to energize this, and once it is energized, now it is in plus V. It has this C is in plus. The switch is in switch. I'll write it as S, not C. The switch S is put to position 1, so that we get plus V volt, and we are able to rotate it in the clockwise direction with n RPM. Now I am trying to give an input to the system that saying that I want an anti-clockwise rotation of the motor with n RPM. So what happens that an equivalent current which has to energize the relay in the opposite direction, so as to bring the switch to 2, has to be given. Okay, so even if the input is given in the opposite direction, what happens to the relay? It is actually, the current is flowing initially in this direction. So now the current has to flow in the opposite direction. This relay, it has to de-energize and then energize in the opposite direction for the switch to go and touch to. Okay, so till then there won't be any switching of the switch to position 2. It has to de-energize, so it will wait till it de-energizes and then energizes in the opposite direction, and then suddenly once it happens, it switches to the next position. This is position 1 and it switches to position 2. So once it switches to position 2, it runs it n rpm in the anti-clockwise direction. Anti-clockwise direction. Here it is in the clockwise direction. Okay, now once it switches here, again I am trying to give n rpm, pause n rpm in the clockwise direction. Again what happens? It has to de-energize in the opposite direction and then energize in this direction for the switch to activate and then move to for the relay to activate and then move to position 1. So what happens that it takes some time so that it moves to position 1. So in fact, this is in fact a relay with pure hysteresis. Okay, this is an ideal relay. This is in fact a relay with pure hysteresis. With a pure hysteresis. This is a relay with pure hysteresis. Okay, now we will see the next figure. Next kind of nonlinearity that can be caused in relays. For example, a relay with deadzone. For example, here we had seen an ideal relay. Suddenly when we had switched on, it has gone to position 1. So now even if I give an input of n rpm, it takes some time for the relay to energize. The switch will not suddenly jump to position 1. It takes some time for this coil to activate and move to position 1. So that time is called the dead zone. So usually we have a dead zone in the case of a relay, and it will be something like this. Okay, something like this. The relay with a dead zone is something of this sort. So this is the input to the system and this is the output to the system. So here also I have the input and this also I have the output. So we can also have a relay with hysteresis. Okay, we can also have a relay with hysteresis. So I will draw that also. This is the input to the system and this is the output to the system. So we have relay with hysteresis and dead zone. This is a relay with pure hysteresis. And if we will see a relay with hysteresis and dead zone, there will be relay has to activate, time is taken for the relay to activate, and then it goes to position 1. It can be in position 1 for some time. Then if I try to move it to position 2, it tries to move back and then it comes down to the dead zone because it switches to 0 position and then it comes down. Then it again takes some time to switch to position 2. Then it comes down here. It takes some time to switch to position 2 here, and so that the coil energizes in the opposite direction. Then again it comes here, goes back to this position. There is again a dead zone if we move it in the opposite direction. So here we are trying to rotate in the clockwise direction and the anti-clockwise direction. If we try to look at the characteristics of the system, we study the forward and the backward characteristics and see how it works. We can see that this the graph 1 is a relay with ideal characteristics. The graph 2 is a relay with pure hysteresis, only hysteresis. There is no dead zone in the system. The graph 3 is a relay with dead zone alone. There is a dead zone only for the system. And the graph 4 is a relay showing a dead zone as well as a hysteresis. So depending upon the complexity of the system, we can model the circuit and see, like we can study the circuit and see which kind of a non-linearity we have to choose for this kind of a relay. I have a relay with me, so I will say, okay, I want to simplify the circuit, so I may only deal with, I'll assume that the relay is an ideal one. Okay, so if I want to study more, introduce more physics to the system, maybe I will go deep into studying the relay and see that maybe there is hysteresis in the system. And so I may have to use this kind of a circuit. So this is how we study the nonlinearities, or we try to introduce the nonlinearities in the system. Okay. So we had studied five types of nonlinearities. One is the saturation nonlinearity. The other one is the friction. The third one was the backlash. The fourth one was the dead zone, and the fifth one was the relay. So if we go and look at it, each one, this is friction one. Saturation, this is a friction type of nonlinearity. This is a backlash, and this is the dead zone and the relay. Okay, so now finally I have the last sheet which you have to fill up and tell me what are the different types of nonlinearities that have been from these graphs. You have to identify and tell me what are these nonlinearities. Okay, after watching this video. Okay, so in the next class, we will go and see what are the different types of, we will just start the phase plane method and see what is meant by singular points and equilibrium points and so on. Okay. Okay. Thank you. Stop this video.